So good afternoon, everyone. I'm very happy to be present with you today to present some of our work on optimization of spin glass landscapes using these tools, which are tensor trace invariants. So these tools have been presented on previous editions of the same seminar, so combinatorics and arithmetics for physics. So in my presentation, I would try to not focus too much on the mathematical details, but more maybe on the application, on the connection with the multiple other fields like spin glass, but also a bit of artificial intelligence, and show how these tools that have been presented and explored in other fields like theoretical physics and high energy physics can be used in in other applications. So this work has been done with Parham Radpay, which is a PhD student on his third year, Mohamed Tamaazousti and Vincent Rivasseau, which is here present with us today. My talk will be organized and structured in this way. First, the introduction. I will present and explain what is the problem, what is the model we are looking at, and why are we looking at, like why is it interesting to look at it. Then I will present, give a summary about the random tensor theory, which are like the trace invariant, the tensor trace invariants. How do we use them? How do we compute some of their properties? And afterwards, we will see how can we apply them in a computationable way, because that's, of course, one of the main objectives in this seminar is to see how to compute important stuff using some combinatorics and arithmetics tools. So first, this model is very close to the one presented yesterday by Stéphane Dartois. So what do we have in this case? We have a very simple model because it's enough to include a lot of the important characteristics that we want to look at and that we want to study, etc. And it's easy to be able to approach it from a mathematical way. So we have a Gaussian tensor, the noise in red here, which is Z. So every one of its components is a random Gaussian value. And we add a signal to it. So a signal, which is, we take a vector, which is of norm 1, that we normalize with square root of n is the dimension of the k different axes of the tensor. And we have this beta. This beta, the signal to noise ratio, is very important because it will characterize the strength of the signal. The objective in this case is to be able either to detect or to compute this signal V. And as you can see, if beta is very large, so it will be quite easy. Sorry. But if beta is weak, it will be either very difficult or maybe impossible from information theory part. So we have actually 3 questions given the simple models, and we will see how it can be related to multiple fields. First, above which beta, so the signal to noise ratio, this one, can we, in theory, so if we have infinite computationable power, can we detect the signal? So it is more related to information theory to see which are the detection thresholds above which we can detect the signal. Another question is about the recovery in itself. It's more related to statistical physics because, as I will explain very quickly afterwards, it's an important problem in statistical physics where we have such landscapes which are related to this model and where we try to find the minimum of these landscapes. So we want to not only detect but also recover this signal. And then above which threshold can we efficiently detect and recover the signal. So what do we mean by efficiently? It means that with the polynomial algorithm. So it's with the method that we can compute on a computer. It's not just in theory and without any mean to do it in a concrete way. So as we see, this model has been extensively studied because it's in this intersection of important fields. So let me give you a bit more details about like how it is related in statistical physics. So if you look at the function, which for each v from the spherical from a unitary sphere, we associate this function t multiplied by v. So we have Sn, we can take it Sn on R, and we just compute v multiplied, which will be sum of all the indices of T1 to Tk of Vi1 Vik. So this is a function, and it is actually a high-dimensional and non-convex landscape because there have been many studies, and related to what explained Stéphane Dartois yesterday, for the one who was able to attend his presentation, like there are means using the K-Grice formula to estimate how many minima there are. And actually the landscapes looks a bit close to this one, and we have an exponential number of minima. So we have like this high-dimensional landscape, and where we have like for each range of energy that we take an exponential number of critical points of minima. So it's very complicated to try to optimize it and to try to find the signal which will be the global minimum. And we don't have like, sometimes you have some symmetries that can help us to study it, but in this case it's completely absent. So this is like this kind of landscapes actually like happen in many important systems in statistical physics, in particular the glassy systems, which is quite common actually in general in life, and that's why it's very important to try to understand, because we don't have a very good understanding of the nature of the glassiness and the phenomena associated to it. So this model gives us a very simple model, like a proxy to study it and to try to understand what happens actually in the glassy systems. So we have like some phenomena that happens and open questions, like the glassy transition. For example, when you take the glass and it goes from a liquid to this glass state that we don't understand exactly how, is it like a true phase transition or not? And we have another phenomenon which is aging that we can see, but still not completely understand. So this model is not exactly, does not exactly describe this, all these glassy systems, but it's a very simple case that can give us very important insights. So that's why it has been mainly studied in the statistical physics community. In the computing case, so now that we have like more devices and more powerful computers and GPUs, etc., and larger acquisition devices, we have like all of this new data which is in form of tensor, and that we want to analyze. Now we have like all this power. We can have maybe even multimodal. Let's say that we have a camera with like RGB plus infrared plus some other information like the position, etc. So this will give us data in form of tensor. We also have like so it's not related to the talk before, but in some cases we can use, actually we can use this this work that we did, and we actually used it to do the compression of multiple like neural networks layers, because the layers are in the form of tensor. So we can use like the tools and try to suppress the noise and make this tensor smaller. So because like when you see ChatGPT, for example, just using a prompt, like it cuts like just sending just a request, it uses energy almost equivalent to the power of a laptop device, which is quite huge. So we want to make them smaller, and we want the cost to be smaller. So this works on the combinatorics. In the case of tensors, etc., can be used and have been like successfully used in many of these cases. And from the point of view of information theory, we have also this very important observation that in this model, for the recovery or even for the detection, we observe like multiple thresholds. we have first the information theory threshold, which we call beta stat. So this, in theory, if we have like infinite computational power, we should be able to detect and recover like above this threshold. So this signal to noise ratio. And below that, it's impossible. The information is not does not exist. There is not enough information to be able to know if to be able to distinguish a model with the signal or without the signal. However, there have been other works trying to find algorithms and like computable methods to be able to reach the threshold, but they failed so far. So we have another threshold, which we call beta comp for computability, which is the threshold for which, above which there have been proven with a theoretically proven algorithm that can work above the thresholds with the algorithm, but this leaves us with this gap between what in theory we can do and what in practice we have been able to do so far. And we don't know yet if this gap is fundamental or not. Like, there have been no work saying that indeed it's impossible with the polynomial time algorithm to be able to reach the statistical threshold. So this gap exists and we don't understand it yet. So, and this property happens for this model, but actually for many other models, important models which are like fundamental in artificial intelligence and in computer science. So, trying to understand it and trying to explain why we have this gap or why there is no gap if we find another algorithm that actually works can give us very huge and very important insights for these other problems. So as you can see, so this model, although it's very simple, we have like this noise tensor where we plant signal, has many important insights for different fields that we can try to explore and try to study. And that's what we will try to do now with this set of tools that, as I said, they were introduced on another, like for another objective. So by Razvan Gurau, by Vincent Rivasseau, Joseph, and many other researchers that worked on them. And we will show that they actually can be very useful to study this model. So first, let's introduce what are these trace invariants. Let's say that we have our tensor T, which like k axis, and we define this transformation under this rotation group that for the tensor T, we multiply every one of its axes by this orthogonal matrix. So if we define this transformation, then we can define what are trace invariants, which are scalars obtained by constructing 2n copies of this tensor T. And that should be invariant under this transformation. So we have very simple examples because this invariance can be illustrated by graphs. So let me explain very quickly how it works. So we have first our tensor T. Let's say that we have 3 axes. So this is the first one, this is the second one, and this is the third one. So if I want to have this particular scalar, here we use the Einstein notation, but I will add it. So what I do, I just take 2 copies of the tensor T. I know that the first axis is contracted with the first axis of the second copy because we have a sum over it. So we make a link between them with some straight sign, because here it's like the first axis and the first axis, same for the second, and same for the third. So in this way, for this particular trace invariant, we have an illustration as a trace invariant graph, which is quite simple and very useful actually to use. And in these cases, we always use this Einstein convention, which is when you have the same index that repeats itself, it means that there is an implicit sum over it. So as I said here, for the melodic graph, so the B, the second one, we contract the first index, so we sum over it, the second and the third. And with this, we can have like different invariants. And so there have been like some studies, for example, of the number of the trace invariants for a given degree D. So the degree of a trace invariant is the number of the copies of the tensor T that you have. So, for example, here you have like two copies of the tensor. Here you have 4, and here you have 2. And so Avuhu and Joseph here present and other researchers, they provided the study about the number of this trace invariant. So we have many useful properties, etc. And we have, so, so we have like this objects which are trace invariants, and that you can see them, for example, as a generalization of trace of the matrix. So in the case of a matrix, when you can take the the traces of the power of the matrices, which gives you invariance over another transformation, and in the case of tensor, so this is kind of its generalization. So we have these objects, they are scalars, so we understand that maybe they can help to detect a signal, but to be able to recover a signal, like you can't do it with a scalar. You need a matrix. But okay, I changed the order. So first, let's give more information about how do we compute the different moments of this scalars. Like if we have Gaussian tensor, as we said, we can actually compute its average, its variance, etc., and many other properties. So this has been this is extracted from the book of Razvan Gurau. So to be able to compute let's say the expectation of scalar, let's say the melodic one, we need to first find all the covering faces of the graph, and then compute the covering graphs and then compute the faces. I will explain, of course, in a bit more details. So let's begin with the tetrahedral graph. So this one above, and as we saw, it's this. Sorry, it's the C1. So given this graph, we want to compute its expectation. So first we find. Thank you. So first we search for the covering graphs. So what are the covering graphs? There are other different ways to add this gray propagators between the different vertices of the graph. So in this case, given that we have 4 graphs, we can put the propagators between these 2 vertices and the one below, like this or like this. Next, once we have this covering graphs where we put the propagators, we need to compute the faces. So what are the faces of covering graph? Is every time we keep only one color on the propagators and we compute how many faces we have. So in this case, so we have 4 faces. And in the end, this say that this covering graph gives us a contribution equal to n power 4. And this gives us a way to compute the expectation. I can give you another example for this simpler case. So given that we have like this this melodic graph, first we add we search for the covering graph. So there is only one way to put a propagator, so it's between these 2 vertices. And then we compute the faces. So we keep only, for example, the color gray with the propagator, and actually this and this. There is only here like one closed phase, one here and one here. So it gives us an expectation, a contribution to the expectation of n power 3. So this is the expectation of this invariant when we have a Gaussian tensor. Of course, we can do it for expectation. We can also do it for variance, because in that case, we just need to take two copies of the same graph like this and search for other converging graphs, so the way of doing propagators, and of course remove the expectation squared. So with
something, when you say propagator, do you mean that you take trace somehow?
So
what is the propagator exactly?
Yeah. So here we have like this tetrahedron.
Oh, it's a Gaussian. Okay, yeah.
And here it's like the gray graphs. It's when you write mathematically the way of computing the expectation of a Gaussian, then you can see it as you can illustrate it, or you can consider it as a propagator.
Okay. And you're assuming these tensors are defined with the graphs. You're not making taking an arbitrary tensor and trying to find that graph composition, like a tensor network or something.
So these are kind of like specific cases of tensor networks.
Okay, yeah.
So you have a tensor, and you can compute like so the trace invariants are tensor networks, but with this constraint. So they have to be invariant. I always confuse between the the button. Yeah. So they have to be invariant under this transformation. So the trace invariants are like tensor networks. So tensor networks are, you take multiple copies of the tensor and you kind of like contract different indices, but in this case it's more restrained classes, and we can see that it's very useful because it allows us like to compute more easily some properties, and we will see that they are very helpful to achieve what we want. But indeed, it's very important to mark this are like a more restrained class of tensor networks. Okay. So as I said, so this are like the trace invariant, they are scalars. So if you want to detect a signal, it makes sense, maybe like with a scalar, to see the distribution of the scalar, like it's the deviation from what we expected. But if you want to recover the signal, we need a vector. So in this case, we need to compute a matrix. To this effect, what we introduce is constructing a matrix out of trace invariants. It's very actually easy. We just take one of the axes, for example, here for the melonic graph, we just cut one edge, the blue one, so associated to the first axis of each tensor, and this gives us like two free indices, so it's enough to be able to index a matrix. So we have like this graph of trace invariants, and we have matrices associated to them, and we have all these properties that have been like provided by all the researchers on the high energy physics that did on the number of this graph, the properties, how to compute the moments, etc. So how are we going to use this graph, this tensor invariant? Because as we explained at first, we said we can compute the expectation and the properties if we have as an input a Gaussian tensor. But in this case, given that we have a signal, we have to redefine some important properties and see how we can use them. So as I said, in this case, like our tensor will be the sum of a Gaussian tensor plus the signal. So we give them like different symbols, and we can decompose a trace invariant as a sum of the pure noise matrix, or invariant trace if it's a scalar, plus other contributions that comes from the signal. So yeah, again, we have like this different graphs, this different invariants that have been introduced for the Gaussian tensor. In this case, given that we have signal, then we have like this part of associated to the signal, to the noise, sorry, and this new contribution that come from the signal. And as you can see, or maybe easy to use, the idea will be to see how this new contribution will be able to how this new contribution will be able to give us enough information either to detect the signal or to be able to recover it. So in this case, for example, we can have like three phases. If it is if it is the part associated to the noise that is dominating for a given beta, so if the beta is very small, this will be the one dominating. In this case, we won't be able to distinguish the noise from the signal. And if we have the second one, which is dominating, then this is a mix of the noise and the signal. We'll be able to detect the signal because it will give more contribution to the highest eigenvalue, etc. But it will not be directly related to the eigenvector in itself. So these are like a mix of different vectors. And if it is the third matrix which will be dominating, then we can the largest eigenvector will be directly related to the to the signal. So as you can see here, so the way of estimating which one is dominating will be to compute the expectation and the variance of every one of them and to use some mathematical tools. We have to extend the definition that we gave. So here in this case, what we explained works only for the tensor, for Gaussian tensors, but we can adapt, and we adapted them by taking into account that some of the vertices are the signal tensor, which are not Gaussian, and they just give a different way of computing the expectation. It doesn't change fundamentally the way you do the stuff.
Sorry, Mohamed, can you go back to your different things? Perhaps it's just a typo, but I want to be sure. The beta, should it be also, going into the it's only located there? You only put a beta on the second term there.
Yes, there is indeed a missing.
Yes, it should be over there. Okay, because okay, good. Sorry.
Oh, it's yeah. So indeed, because the beta needs to be here, because then, when the beta is largest, then the terms will be more dominating. They are not independent of beta. Otherwise, it will not be very helpful. Thank you for the time. So using this gives us an algorithm. So we have this tools and that we can use, and they can be computed. And actually, they are the good thing. They are very easy to compute on the GPU because it's some sum that you can parallelize with the GPU. It can be extremely fast. It takes some seconds on a laptop, which is very useful actually, this combinator X objects. And the idea is just to compute the trace invariant. So we construct, for example, given the tensor, we compute this subject, and then we compare it with the variance and with the distribution of this object for the Gaussian tensors. So if you know that the Moronic invariant trace for a Gaussian random tensor gives a distribution like this, and you compute your scalar, and you find it very far from this distribution, then you can detect the signal. So this is just a simplified way, but of course you use the Chebyshev theorem to be able to give exactly the uncertainty about how the probability of the presence of a spike. Now let me introduce another graph, which will be important to give some theoretical proof of the different thresholds, which is the maximal single trace graph. So in this case, it's for n equal 5. So it's quite simple to define. The important thing to keep in mind is that we have a conjecture about its expectation, but I'm not sure, but it's still not verified yet. So we know that it's up to k equal 12. This expectation is correct, but for above than that, we don't know exactly. We don't have a theoretical proof. Another important graph is the generalized melon. So the generalized melon is to take the same graph and copy it, and we can compute its expectation, and we will see in the theorems that come that this is also gives us this computational threshold. So it gives us the beta comp below which we can't detect or recover our signal. So we have, let's say, 3 results. So using the algorithm 1 and 2, it's the algorithm for the detection of the recovery. So if you take the Melonic graph, which is the easiest one, you can reach already like this computational threshold. So this is the threshold which is the best for the existing methods. So many methods have been suggested, and the best of them have been able to reach this threshold in particular, and the Melonic graph is also able to reach it with quite fast time. So we have like given with the theoretical proof, and it's very easy to compute, as I said. There is also another graph, another algorithm that can be able to do this, to reach this threshold. And for the case of larger order of tensors, we know that the perfect one factorization graph is able to reach also the threshold. But of course, if this conjecture is verified. This tools also can be very useful to even generalize the model that we had, and to obtain results that have not been obtained by other methods. So if we consider the case of a tensor for which the different dimensions are different. So this happens in concrete case. So it's not enough just to consider the case where other axes have similar dimensions. And in this case, like when you use the Melonic graph, thanks to the very easy tool that we have to compute the moments of the invariants, we can obtain this new thresholds, like for this case, which is the maximum between these two quantities. It depends on the number of the dimensions, and with the new thresholds. So there have been like the state-of-the-art method that have been suggested, and this slide is to explain about the power and the versatility of this framework. So in this framework, we had like this. We suggested to use like the state invariants as a way to provide algorithm to be able to detect or to recover the signal. As I said, like other methods have been previously suggested and proposed. And we can cite like the 2 main ones, the most successful ones, which are the tensor unfolding and the homotopy method. Tensor unfolding have been suggested from a point of view of algebra. So this was like the motivation of studying this method, and the homotopy method was based on some homotopy insights that they wanted to use for this case. And one very interesting and observation that we can see is that these two methods that have been suggested from completely different point of view are actually the same. They correspond to the algorithm associated to the Melonic graph and the tadpole graph. So if we take outside invariants, we take the 2 simplest ones, the ones of degree 2, so the Melonic and the tadpole ones. We see that the 2 methods that have been proposed and that are the best to work on this model, they correspond to this state-of-the-art models. So it's very interesting. It shows the power of expressivity of this method, and it suggests also to us like what happened then if we take if you go further than degree 2. If already the 2 simplest methods corresponds to what exists. So what about if to look like above the degree 2? So we wanted to study this new method based on the tetrahedral method. Here I just give some numerical experiments, and we can see that in blue we have like this tetrahedral graph, in orange the Melonic, and in green the homotopy. Here, of course, I added the variant for each one of them, so I'm not going to go into details, just improves a bit the results. But we see that it was enough to go to the next graph to be able to do better than the existing methods. So this frameworks is able to not only incorporate existing methods, but also propose new method that works better. So now I will talk a bit about previous approaches that also involved graphs and tensor invariants. So first they have been used by Oleg Evnin to study the highest eigenvalue of symmetric Gaussian tensor. So this is close to maybe what's presented Stéphane Dartois yesterday, but Stéphane Dartois considered a more complex case because you can have a complex tensor and with the other properties that he's studying now with Parham Radpay. But using this graph, you can have an estimation of the largest, highest eigenvalue of symmetric Gaussian tensor. Then Razvan Gurau provided generalization of the resolvent of a matrix to the tensor case. So the resolvent in a matrix case, it is a function that has singularities in the eigenvalues of the matrix. So it's defined with some normalization, of course, of trace of 1 over omega minus id minus m. Yeah. And if you want to generalize the resolvent to the tensor case, he suggests like a generalization. And he showed that this gives us a way to be able to reach this threshold, the statistical beta. So he showed that if you take a Gaussian random tensor and you put n to infinity, this resolvent, and for beta above this beta statistical, shows a transition of the largest eigenvalue. In the case of tensor, so it's not exactly the eigenvalue, but largest singularity of his generalization of the resolvent. And he showed that the generalization of this resolvent can be put as an infinite sum of trace invariants. So when you sum like some kind of trace invariants, you have this new function that is able to reach the statistical beta threshold. However, this function, this resolvent, is not computable. So we don't have, it requires to compute integral of over a dimension of over a space of dimension n. So it's exponential in n, and the infinite sum also is not very computable. But it reaches this this new threshold. So what do we obtain now? Like what we can see is if we use only one trace invariant, we know theoretically that we can reach the computable threshold, which is like the threshold for which like the best algorithm reached so far, and that can be computable, and we have the theoretical proofs. And then if we use here in this case an infinite sum of some of this trace invariants, then we can use like this theoretical thresholds, but it's not computable. So what we, given this facts, what we wanted to do is to study the sum of graphs. So what happens if we don't do an infinite sum of graphs? What if we sum just a finite part of graphs? Maybe like if we choose correctly, given some properties, etc., maybe we can get close to it, not necessarily reach this theoretical threshold, but this gives us a motivation and incentive to look at what happens if we sum some of this trace invariants.
Sorry, Mohamed, the beta computational, this is the one n to the power n divided by 4. Am I correct?
Yes.
and k to the 4.
Yes.
What about do you have a theoretical estimation of the over beta? Is it?
Yes. It's so this have been by information theory. It's like it's 1. Of course, it's 1. Like depending on how you you normalize your beta. So it's 1 if you put a square root of n next to the beta.
All right. Okay.
So if you have a Gaussian tensor, every component is a normal Gaussian variable, and you have a square root of n, so it's around 1. And in this case, it will be, let's say, 1 over 4 in the case of k equal 3. So if we have a tensor of 3 axes. So it's 1 over 4, and here it's 1.
Okay.
So, and we have this gap that grows with the dimension, like infinity with the dimension, but we don't know.
Nobody can. There was no attempts for, no theoretical attempts from this beta comp to the beta that other one.
So this is like a very important question, and this very big motivation of why people are still exploring it, because this is like a statistical computation gap that exists, and it doesn't exist only in tensor PCA. It exists also on these methods like sparse PCA, pointed click, random constraint satisfaction problems, and many others. And we don't understand yet. So there are many approaches to try to understand. So some of the people try to look at some classes of the algorithm and show that for these classes of algorithms, then we can teach this. And like it has been proved, for example, for some methods, it has been proved, for example, that if you use only a polynomial product of the component of the tensor, so there is no possibility to be able to reach this. So they try to remove, like by some classes of algorithms. Another approach is to make some connection between other problems and try to say, okay, we can show that if this in this problem we can prove that it's not possible, then like directly we can say, but still there is no definite answer so far. Like we don't know yet if it's like a fundamental gap that like we can't. There is absolutely no way theoretically to use a polynomial algorithm, or if it is just because we still didn't find yet like what works. And it could be very interesting to understand like what works, because then it has been shown that if we find a way to find an algorithm for this, we can directly generalize it to many other important algorithms that and many important problems in computing science and applied mathematics. So it's people are looking at it, but without. So far, still it's not very. We don't have any conclusive results. So I will try to be very fast. So we wanted to look at the sum. So with the Parham Radpay. What we did also, if we take a case of a tensor where we have the same dimension, we can construct axes of different dimensions, and we have a larger number of this graphs. So, and we can reduce actually the numbers because there is some repetition and some redundancy in this graph. So there is like this combinatorics studies that have been done by Parham Radpay to try to understand like how can we know which are the graphs that doesn't repeat themselves, to know how to sum them. And also when we sum these different graphs, like what coefficient do you put to which one? So do you just put them all together with the same weight, or do you give different weights? So it depends. So that's what we are looking at when you compute. We try to define this difference of the average of the distribution over the variance, and with this method, so we have like some combinatorics results that we use to try to optimize which sum is better. I will try to go. So this is to show how we can improve the results with the sum of some graphs, and how we can actually not necessarily take all the existing graphs. Here, like this graph is mainly to this illustration is mainly to show that In orange, we have the sum of, from what I remember, like 100 graphs. But if you stick to some fundamental graph that you try to distinguish, and that gives a larger contribution, then you can decrease largely the number of these graphs without reducing a lot of the accuracy. So there is all of this question of when you have like the first trace invariant, and the second one. When you do the average and the variance, there is, when you try to compute it, you have to take into account, for example, this, to compute the different properties of a product of different trace invariants and which one maximize the expectation while minimizing the variance, etc. So there are all this property that I don't have the time to go into details. So I will just go to conclusion because I'm over 5 minutes. So we have this new framework based on this tools on the trace invariants that as have been remarked, they are like this smaller class of tensor networks, but with a very nice property that gives us this option of compute some expectation and variance and to have like very easy theoretical proofs, and that allowed us to give to generalize some results, for example, for the case where the axes are different, and where we had like this framework which proved very interesting because it was able, when we look at the two simplest trace invariants, they were like corresponding exactly to the two state-of-the-art methods that have been introduced from other backgrounds. And when we looked above that, like for a larger trace invariants, we were able to obtain better results. On the other side, there have been other works that looked at kind of infinite sum of the sum of the trace invariants, and they have been able to reach this statistical threshold. Why we showed that with only one trace invariant, it's actually impossible to go below this computational threshold. So what we looked at is what happens if we sum not an infinite number of them, but just a finite one of them. And then like the questions are which invariants do we sum, how do we choose them, how do we choose the weights, and we have obtained a way, some Parham obtained some criteria showing that you can reduce largely the number of graphs and trace invariant that you sum without reducing the accuracy that you obtain of the sum. And of course, the objective is to continue this work and to maybe like get the closest possible to the statistical threshold. So also just a point, this has been also been used, as I said, for the compression of neural networks, and just also to give other, to make a relation with other fields, to show that because these tools have been presented on, as I said, on previous editions, but on the high energy physics, and I just wanted to show that these tools also are very powerful and can be proved very useful in many other applications. And we are actually using them in the collaboration of Vincent Rivasseau with the CEA, where they study more on the applicative fields. Thank you very much.
Thank you.
Are there questions, remarks, comments? Whatever. Yes?
Yeah, just a question.
Yeah.
So in this case, do you assume the graph is an ansatz? So you say, this is the graph that I want to look at for the composition? Or can you learn the graph somehow and find which is the most appropriate graph for a given task?
It's a very, very interesting question. So in our case, as I said, the first thing that we did is just to look at the simplest one, because actually there are not as many. And for the invariance of degree 2, we have like these two ones. So we said, okay, let's begin by looking at the easiest one, the simplest one, without having a criteria or like going to more sophisticated choices. And already we saw that they correspond to the state-of-the-art algorithm again. So we wanted to look at more the invariance of degree 4, and we saw that it was better. but when we want to look at the sum of the trace invariants, then yeah, the question of how do we choose the invariant? How do we choose the graph? Which graph is better? Like which have the best properties? Like which one is more adequate, etc. This like in this case, yeah, we began looking at this and we obtained like some interesting results as I presented very quickly, unfortunately. But yeah, like this idea of not just taking anyone, but having some criteria to choose which one to use, because indeed they are not all equivalent. So there are very good ones and there are very bad ones. And yeah, Parham Radpay like studied of when you sum them, which graphs do you sum and how do you use them. And in this case, indeed, we began looking at more sophisticated choice. But already just with the very simple choice, as I said, like we obtain like the existing methods and we can already do better than what exists.
Other questions, remarks, comments? Yes,
yes,
Joseph.
So, taking again there, so you according to Razvan works, theoretically, he said if you take all the graphs, the infinite sum of them, or is it just a conjecture that you're going to reach this B stat?
No, so it's not all the graphs. So he studied the resolvent, like the generalization of the resolvent, and he showed that it corresponds to a sum of certain graphs. So certain graphs that he presented and he introduced and explained. Okay. So it's equivalent to that. Yeah. And he showed that indeed you have like this because the resolvent, so you have like this finite number of singularities. That is when you take a Gaussian tensor and you put n to infinity. And when you reach this statistical, he showed, yeah, mathematically, it's not a conjecture, that you have this jump, you have this of the largest singularity. So it's kind of equivalent to the matrix case. So in the matrix case, you have like this Wigner semicircle. And when you have like this threshold above which you have like one of the eigenvalue that pops out, and the singularity that goes out, so it's like the equivalence, but it has been proven recursively in the works of Razvan Gurau. So he looked at the case where we add a signal, and for a given beta, he showed that that's why I put sum. So it's not the sum of all the trace invariants; it is infinite sum, but just for like the graphs that he introduced.
So it's an infinite sum, but not all of them. Yes. Is what you say. Yeah. Okay. And the one that you choose in your finite sum are of that type.
No, we looked at yeah. So we looked at, because the idea is, yeah, like to, again, that's also one of the objectives, I guess, from the seminar, is to look at the way to make the stuff computable. Yeah. So we began looking at the simple, but then like the lowest degree, and try to choose with some criteria how to sum them, the weights, etc. And this, like, again, has been done by Parham. He found like the weight to put depending on the type of the graph and etc. Like the very nice result that you obtain.
So what you have shown is okay. This type of invariant are still okay because you reach this beta comp in any case. So you are safe on that side. So you can play with that type of building blocks. Okay.
So we did this, and we know this is like a motivation, incentive. We know that for a given, if you sum infinite sum, you can go, but you can do it in practice. So we said, okay, let's begin step by step, and this is what we began doing and improving the results.
Is it when you want to implement all these invariants? Does it cost you much? You say it's fast, but I guess you want 100, you want 200, right? You want to go there, right?
It's a good question, because indeed, the more you add the degree, the more you increase the degree, the harder it is. And that's also one of the motivation of what Parham did when he chose like much smaller. For example, here, you have like 28, and in this case it's I guess only 3 graphs, and with a very small loss of accuracy. But indeed it's a very good question that okay, it's computable, but then like you have this this increase of costs, and so it's also like motivate even more to try to make a better choice, like to be more rigorous on the choice of the graph that you are looking at. But yeah, there are also like other works done by professor, I forgot his name, but using more tensor networks. So on this, and he showed like a similar results to this. They looked as well as a similar model, and with tensor network they have been able to show that in this direction it can maybe reach this statistical gap. But for now it's not exactly the same graphs. It's not, but it's more as motivation, so an objective, and we want to take a step towards.
What people think? Is it some will? Is it? I mean, what's the belief? The general belief, you know.
So in general, people believe that it's fundamental.
Okay, the gap is fundamental. This is what people.
Yes,
okay.
Yes. This is the majority, the major belief. But people have different opinions.
Other questions?
I will let you go back. Thank you very much for your attention. And thank you for